The Monty Hall problem has been brought to you by Group B5, Colin Peterson, Alex Stephen, and Mohammed Asghari. For more, good morning, boys and girls of North Campus. This is Mohammed with Channel 203, The Leaders in Logic. Today we'll be explaining the Monty Hall problem. In the Monty Hall problem, we have our game show host, Monty Hall, and he presents to you three doors. Door 1, Door 2, Door 3. And you have to choose one of these three doors, hoping that behind the door that you chose, there's your prize, be it a beautiful new yellow Lamborghini or $1 million, anything. But two of the doors are busts, and you won't win anything, or a goat, whichever you prefer. But taking care of a goat in itself could be a bit of a hassle, so I'd go for nothing in this case. And Monty Hall, after you choose your first door, will open one of the remaining two doors and show you that it's empty. And then you get to choose whether you want to switch to the other remaining door or stay with your original choice. Most people at this point would be like, okay, there's a 50-50 chance that it's either with the door I have or it's in the other door. But we're going to show you that it's always better to switch, that your probability of winning will always be higher by switching. To get a more intuitive sense of this, imagine there's 1,000 doors and you choose one of those 1,000. Then Monty Hall comes and opens 998 of the remaining 999 and gives you now the chance to switch to the last remaining door. Most people at this point would choose to switch because they don't trust their first choice, because who's going to get it right out of 1,000 doors the first time? Now Colin will clarify to the more quantitative reasoning of why you should always switch.
Thanks for the introduction, Mohammed. Let's go back to our three doors. We'll have door number 1, door number 2, and door number 3. Now, you're going to select a door. Say, we'll call it I. So, after you select your door, Monty Hall will open one of the two doors you did not select. So, we will say that M is that door. So, for example, if M equals 2, that means 2 will be the door that is opened. Alright, and then we will say W is the actual door that your prize, in this case the car, is behind. So in this case we'll say W equals 3, just for example. So that would imply that 1 and 2 have goats behind them, and door 3 has the car. So we are going to use Bayes' theorem to figure out exactly what the probability is that you get the winning door by switching. So let's start a new slide here. Alright, so the probability that the winning door equals K for K of any of the 1, 2, or 3 doors is just 1/3. Now, the tough part are these conditional probabilities. So, the probability that Monty Hall opens door M, given that given that the winning door is door K, needs to be split up into 3 different parts. So if I, J, and K are distinct, meaning that the door you pick is not the door that Monty Hall opens and is not the one with the car behind it, then if you switch, that means you're switching to the one with the car behind it, so your probability equals 1. Now, in the other case, where J equals K, or J equals I, so that means that the door that Monty Hall opens is the door you selected, that's probability is 0, and the probability that the door opened is the winning door is also 0. So we can write that. And in the final scenario, if I equals k and j does not equal I, that means that the door you chose is the correct door and the door that Monty Hall opens is not your door. The probability of that is 0.5, since we are going to assume that Monty Hall chooses randomly which door to open. Alright, so those are what are going to make up the denominator of our Bayes theorem. So we're going to go to our next page. Okay, the probability, we want to figure out the probability of winning, that we have the winning door given that the door he opens is k, for all I, j, and k are distinct. So that means on the top of our equation we will have the probability that m equals k given w equals j for the distinct case, which in this case is 1. And we're going to multiply that by 1/3, which is the probability that the winning door is j. And then we will divide that by the sum of the probabilities in our previous page. So we'll do 1 times 1/3 plus 0 times 1/3 plus 1/2 times 1/3. And this equals 2/3. So this is saying that if I, k, and j are distinct, so you chose door I, which is not the winning door, and it's not the door that Monty Hall opens, then your probability of winning, if you switch, is 2/3. If we compare this to our original calculations, that the probability of selecting the winning door equals 1/3, this means by switching, we double the probability that we win the car. Now I'm going to send it over to Alex for a more general view.
So here's the original Monty Hall problem. 3 doors and 1 Lamborghini that looks awfully like a school bus. So now let us assume that there's more than 3 doors. What if there was 4, 5, 6? In fact, let's actually assume that there are n doors, where n can be any number. And also, if you're going to have that many doors, you should probably have more than 1 car, or school bus type thing. So we're going to assume that there are m prizes. So m cars, m $1 million. And the only way that this can hold true for the Monty Hall problem is if the number of doors is greater than or equal to the number of prizes plus 2. So let's go and let's try to give an equation that will calculate the probability of winning when you switch and show that this is always greater than the probability that you will have normally. So let's look at the Monty Hall problem again. 3 doors, 1 car. But let's assume that there's 4 doors. What about 5? What about 6 doors? In fact, let's just say that there are n doors, where n is any positive integer. So at the same time, we can also assume that there's more than 1 car. There could be 2 poorly drawn cars that look like school buses, maybe even 3. So in fact, we're going to assume that there are m prizes, so cars. And to make sure that the Monty Hall problem still holds true, the number of doors must be greater than or equal to the number of prizes plus 2. That means that you always have at least 3 doors and 1 prize, just like in the standard Monty Hall problem. So now we're going to derive an equation that shows the probability of winning when you switch, and show how it's always greater than the probability that you have when you just do the problem normally. So, keep going. So, the probability of you guessing a car on the first try is m over n. Now, we can also say that if you do guess a car on the first try, there is now 1 less car, and since Monty Hall reveals a door, there are now 2 less doors. And we can add on to that the probability that you don't guess a car on the first try. So that's every other possibility, so that's 1 minus m over n. And we can multiply that by the fact that now you still have m cars, or m prizes, but now you have 2 less doors. So we're going to go ahead and actually take this equation, write it down just a bit, 2m over n multiplied by n minus 1 over n minus 2, and you can go ahead and do all that algebra at home. But this shows, since n minus 1 is bigger than n minus 2, this constant is going to be bigger than 1. So that means that you're taking m minus n and multiplying it by a constant greater than 1. So that is always going to be bigger than the standard probability of m over n. So this shows that when you switch doors, your probability will always be greater than when you just randomly guess a door. Well, thanks for that. Now back to Mohammed.
Thank you, Alex. Well, you guys know how to win in Monty Hall's game show now, but I already have, and I'm going to drive away in my new Lamborghini. Have fun in Arbor.